Okay, you can hear me? Thanks, fine. So it's a pleasure to be here after some years again. I welcome you to our presentation, which is really storage focused, and this is our view of all the NVMe things that are happening in the market. And we will go into some details. And what we see is really, sorry. What we see is there is so much publication and efforts in the industry about NVMe that we found, okay, the old title of ABBA, The Winner Takes It All, is the right way to make a quick positioning where we go. So let's look at the brave new world of storage. So what does IBM ABC does? ABC is on the road since 1981. We have 30 years of experience with storage. And you see our old colleagues on the right side. And the focus has always been to provide zero failover fallback of a synchronized mirror of the storage. So we never have been working with primary, secondary, which we saw is mainly in the SMB market a nightmare. So this has been the focus, and these have been our companies we use. So the topic or the focus of us is to provide the truck, just to have a perfect platform, and with or without driver. So we do remote management if you want to, or you just take it as a complete solution from us. So that's our focus, to have high available and high performing infrastructure. So in 2012 was a elementary decision to go to the server-based storage, because Dell was one of the first who brought the disk format of 12 or 24 drives in 2U units combined with CPUs. Then we said, okay, we have more than enough bandwidth you can't find in a storage system. And then at the same time, we saw the upcoming of NVMe PCIe SSD. And we never used the SAS or SATA SSD at those times. We immediately changed over to NVMe because we said, okay, then we can take full profit of NVMe technology. And then we saw also is a change from the traditional storage server, where you have data centers full of drawers with disk drives, instead of having just a small computer with NVMe. The recipe has remained the same. Take as many as possible of standard components. The only innovation is just to select them and to evaluate them. So there's nothing behind, because a main thing is to keep support trivial and not to have too many things integrated. So this recipe is still keep it simple and stupid, and this was what we have done in 2012. And the interesting thing is when we used those NVMe PCIe SS drive, they have been foreseen with a one-day disk write, but up to now we haven't seen in no installation even to start with using the reserved blocks of the NVMe's. So we still work with the standard blocks, even in an Oracle environment. Now, 6 years later, we have very interesting things coming up. We have obviously the PCIe's, and we have the UT format, 2.5-inch hot swap. So whether you need hot swap or not, I think it's a little bit a tribute to old storage thinking, because you have been used to have replaceable drives, but one should remind the flash technology is more close to memory technology, and I'm not aware how many servers are around where you have hot swap memory. So, but this is a way the industry has chosen. Now there are two new formats. This is one, the ruler format was initiated by Intel. The idea was to become more efficient and to increase the capacity. So the ruler is now available with 4 and 8 tera and is expected to end with 32 terabyte per ruler. Then another initiative, so the EDSF means Enterprise and Data Center Small Form Factor, which will be now standardized. And then the initiative from Samsung is the next generation small form factor, or also M3, but it's not, it has other sizes than M2. And this goes up to 16 terabyte this, at the moment. M2 is interesting because you save space, and the funny thing is, on all the new notebooks you have NVMe drives, and when you go to the server, then you say, okay, where is my NVMe drive? So you have SATA and SAS drives. So the important thing is to make better reliability. So you have no longer cables as you have with the U2. You have less components because you don't have the enclosure of the flash disk. And the backplane is rather tricky because you need holes for temperature problems, for thermal problems. And now thermal problems are reduced at half as a much more efficient SIS technology. And that's the main boost. And what we see coming here is very interesting. Even they are already available. So the NGSFF we can already have, and also the ruler now. Then it's not enough just to have the standard flash technology. Intel did a good job with the Optane technology you have already heard and you probably know, where you can accelerate things in a tremendous way. And you see the up graph on the left side. You can really speed up, and it's an excellent thing for metadata, caching, databases, and so on, really to speed up tremendously. So we have a lot of tools and possibilities, and when we even look at older, so 2 years old, such comparisons, you see there's a tremendous boost of performance. It's between 6 and something over 10 of improvement in performance, IOPS, also throughput. So NVMe is the protocol that has been really defined to take full profit of flash technology. And you also can use the SAS or SATA interface, but it's not the adequate technology. So you give away a lot of the potential of the technology if you restrict yourself to go just with SAS or SATA SSD. It's extremely efficient because you have a smaller instruction set and you have a lot of commands which allows the 64K command queue in comparison to SAS and SATA allows for parallelism, which makes it even more powerful. So the interesting thing now is when I take a single NVMe, I end up with almost 4 GB of potential throughput. This may not be achieved with any of the current products, but one is quite close to this figure. And you see with increasing number of products and new technologies, it's also important to go over to PCI 4. And for instance, if you take the layout of a motherboard, then you see the CPU lanes, they are directly connected to the CPU, CPU1 in the bottom, with 4 NVMe directly attached to the CPU. So the shortest way is normally the fastest way. And compared to traditional SAN solutions where you go from CPU to bus to fiber channel HPA, switches and so on, so you almost retire in comparison to the really directly connected NVMe on the PCI bus. And you see now the NVMe uses already 4 CPU lanes. While the Broadwell came with 40 lanes, Skylake 48, and the interesting thing now is in this environment, mainly for storage things, is the AMD EPIC CPU coming with 128 lanes, giving you another dimension of using NVMe to be more efficient and effective also. So you see, we have improvements between 6 and 7 times in bandwidth, in IOPS. These are old figures, 2 years old. Maybe there are better NVMe now around, but I think the main thing is to see there's a really boost in technology and in performance, what you can gain with the new technology. The problem, you could say, is now the CPUs are too weak for NVMe. So flash technology is far ahead of CPU technology because you can't provide enough lanes. The Skylake comes with one CPU. One CPU has 48 lanes. You can't use all because you need UPIs between or peripheral things, and while one NVMe occupies already 4. Now the manufacturers look how to improve things and say, okay, we have the F version of the CPU where we connect with a QSFP module to some fast environments using OmniPath technology. This is an approach from Intel to compensate, I would say, in a black-white picture, to compensate a little bit lack of CPU lanes. Now, AMD has a very good approach now for NVMe, mainly when we think that a single socket is very effective for a storage box, so you don't necessarily need to have 2 CPUs. And when you see NVMe takes 4 lanes, so there's a different font loaded as usual. Sorry, huh? So NVMe, we have 4 lanes and we use almost 90% of the bandwidth we occupy with 4 lanes. So we have to be careful what we are doing with our lanes now. And if you see on the bottom, does it make sense to go any longer with 10 gig? Because this is really a waste of capacity, because you only take 32% of the potential of your lanes available. And so it's difficult to understand why people not finally change over to at least 25 gigabit, which is in most cases cheaper. It's simpler, mainly when it comes to the new 100 gig standards, because you have 2 lanes only for, or 2 cables, let's say, 2 cables for 25 gig instead of 2 cables for 10 gig, and then you end up, for instance, with much lower number of fibers when you go with 100 gig than with the old 40 gig. And the interesting thing is how now that you can have direct connected point-to-point connection with SATA up to 32 SATA drives directly connected to the CPU. I think Skylake is around 14. And but you see, okay, you can do it, but you only use 5% of the lane. So you give away another potential of performance, you throw it away, and you have to think very well about whether to do it or not. So this shows now it's a very interesting and challenging job to evaluate the basis for your NVMe machine. And you have maybe 3 focus. Maybe one is capacity, one is IOPS, and another is throughput. And when you go with capacity, you could say, okay, for cost reasons, I take those 32 SSD, SATA SSD, and then I get 192 at a very attractive price. And if it comes to IOPS, then you still think about non-volatile RAM, because you gain extreme IOPS. But you see, you need, as soon as you need a certain capacity of NVMe, you very quickly match figures of the NVDRAM with your NVMe drives. This is the middle column. And then if it comes to throughput, you may have more 100 gigalanes. And, but now you see, when we go with 100 gig, and one NVMe takes almost 4 gig, and this 300 gig is roughly 30 gig. So you see, you may have 3, maybe to 4 NVMe per 100 gigabit link. So one has to really evaluate what does make sense. And since we have a bottleneck with the number of lanes, it depends to choose and to select very well the platform, what you are using for your purpose. And that's the reason why we distinguish between the universal department store servers. You can do everything, but maybe for your purpose they are oversized or wrong-sized, which may have impact on cost, versus purpose-built servers for efficiency. That's what we have learned through the last 2-3 years. When we saw Supermicro having hundreds of servers, we thought, okay, it's silly. But the more you enter in the detail, you see it's not so silly, it's a tremendous challenge. And the good thing is you can really make a layout very close to the customer need. Because then you can choose between machines with so many NVMe, with external connections and so on. And here on the left side, you know, when you're playing with this, when you had only the link, the left side, the door or the window was just a hole, while on the right side you get really explicitly a window or a door as a component. So we have now more than 100 NVMe servers already. This is a very good foundation to find and to evaluate individual solutions, to look into which way you would like to go. When we have a look on those machines available, so there's, for instance, the 1U machine with a 36 next generation SSF NVMe. We end up with 576 terabyte in 1U. Then we have those two systems, 32 times U2, which is a 2.5 inch form factor. Here we have now up to 11 terabyte drives, or on the right side with the ruler, where we can expect 32 terabyte drives on one ruler, which means you can have, on 1U, you have 1 petabyte of NVMe. And now you think, is it still affordable? But if you evaluate, then you have to think, okay, what's the alternative? And maybe you take into account space and expansion of your data center. The problem is only you can't shrink your data center, but you can fill it up with NVMe technology. So then there are other models, which is extremely interesting. For instance, when we go with ZFS, because we have dual port NVMe, 48 drives, and we have 2 servers, and both servers have access to the same NVMe. Another interesting machine is 2U with 4 nodes and having 24 NVMe. And if you take into account that you have already on this 2U node 264 terabyte, so you see you have extreme possibilities to find a very efficient solution for your environment. Or you have the 40 times U2. Or what we wanted to show, unfortunately THL didn't manage to bring those systems here, is the 1U with 20 NVMe with 7mm on one, which is currently the 7mm are currently limited to 4 terabyte, but it depends what you need and how many nodes you would like to have. But as soon as you go to nodes, the middle machine, 2U with 4 independent servers, is really the hot stuff, because you see what you get. You get even 3 UPIs, you have 24 DIMMs, you have 2 Intel sockets, you have 2 unoccupied or free PCI X16. So this is a very, very, very strong offering, because you can use 11 tera NVMe, for instance, here. And what we have seen always, when you take 3 1U machines, not equipped, they're always more expensive than the chassis with 4 machines. Now what we see is storage changes really to server-centric and software-defined. So there are coming up other questions. Now what are we going to do with NVMe over Fabric? Do we have just a bunch of flash? What is RAID protection about? Then we have the solution scenarios are more in the HCI, hyperconverged infrastructure, or a holistic data management. Let's have a quick look at those components. So there is now a lot of developments in the industry. On the right side, you see the main players with the RDMA concept, which is mainly Mellanox providing the basis and the support and the adapters, and also now with the Bluefield NICs, where you can have a system on in a CPU, and allowing to make own developments and to bring more functionality into the network card and to offload the CPUs. Then we have 2 companies in the software environment, which is Excelero and E8. So a little bit different approaches. Excelero is purely software defined, so you use more or less any hardware. This is a step that is planned with E8. So if you want to go more into details, you have here some names. On the other side, there's a huge fiber channel industry, and they try to keep alive in a certain way. So they have also their developments, and whether they will succeed, the market will show. I think when you have an installed fiber channel, very expensive infrastructure, then this may be worth to have a look. Otherwise, I think we know the Ethernet, the world has gone to Ethernet, and yes. Then there is also a JBOF, meaning just a bunch of NVMe flash, also on 1U. And you can have it with the U2 hot swap or with the ruler format. And the interesting thing is now that we do combine for mainly for the HCI environments, we combine Optane technology for caching and using NVMe for capacity. On the right side, you see a system layout we have done with JBOFs, with servers. The problem now is, do you find servers with 6 times 16 lanes PCI slots? And you see it's difficult to find really machines, and you see now the NVMe technology is beyond the server technology. And here mainly we do things with spectrum scale. And what can you do with the JBOFs? You have plenty of possibilities because you are quite flexible to configure. You can configure over the BIOS of the box to have partitioned access to those 32 drives, or you can have shared access. And here you go with this adapter you see in the middle of the system. This is nothing else but extending the PCI bus from internal to an external box. So obviously can't go more than 3 meters, but it will be close to the server system. So you can, for instance, have those 12 single attached servers with this board, and using the board also for with the 2 PCI slots. But the 2 PCI slots open up also the possibility to have here Mellanox Connect X adapters to go with NVMe over Fabric. Then when it comes to RAID protection, there's a basic point. There is a tremendous difference of the reliability when going with flash technology instead of disk technology. So you have to compare the failure rates, and then you see how sensitive is RAID protection in an NVMe environment. And it may depend that you say, okay, if you have a cluster with a lot of drives and things, maybe you even refuse to go with specific rates, or since you are used to have rates, you go. Then it's also important to see you have a much higher throughput, which means if you once have the problem of a rebuild, the rebuild is done in a fraction of the time you currently have with disk drives, which is also a very important factor. Then from the RAID approach, we know it's hardware defined, as you had mostly in the past. The mainstream now is software defined with erasure coding or with the GNR of spectrum scale. And now there's an interesting way also provided by Intel. They call it virtual RAID on CPU. And the main advantage is you see you go vertically to the CPU. And it's a kind of hybrid solution. And you're probably extremely fast. We have scheduled to run the next time the tests and to see where we are positioned with this technology. And it's extremely efficient because you can't be more close to the CPU, and you're between CPU and NVMe drive. So this is an excellent approach and should be taken into account. So what do we have with the solution scenarios? Typically, we have hyperconverged infrastructure. And for instance, here on the left side, you see 8 nodes. Each node 8 times 2U servers, which are the 2U boxes with 4 server canisters, coming already with 6 NVMe per server. And now you can expand those servers with the extension board of the PCI bus to the external JBOD. And you can have down on this 2U machine the 1U JBOF with with NVMe, totally 32. And then you can say, okay, each of those 4 servers gets another 8 NVMe of, for instance, one's available, the ruler 32 terabyte. So you see, you have on 3 units, you have those possibilities, and you can deploy in the for service. You can use maybe also Optane technology to be even faster. And so you have a lot of possibilities in such an environment. So then the challenging thing is also to change over from storing is boring to do something more and to take profit of the ILM engine of spectrum scale, which allows for a logical tiering, which means, for instance, you can have in front, you can have, for the high performance, you can have an NV environment, and in the back, where you have cold data, you may use old storage systems you cannot throw away today. You can still use, and then you can set up rules and to change over with from cold to hot data and vice versa. This is a step what we see is very important, and we have done it already now with GPFS, and you see the picture. It's simplification and it's logical, and the good thing is we don't use an HSM mechanism because the HSM causes a lot of problem because you have sparse files and those placeholders are not backupped, and so this could be a problem, while the ILM engine is really one layer and goes through it logically. Obviously, we combine this with Spectrum Protect. Spectrum Protect we normally also deploy based on GPFS, allowing to remove the entire virtual tape library layer and to get much more performance out of TSM. Seeing all this, we should not forget how things are going. So we can continue with the stagecoach and we can change horses, we can add horses, or we can just use a tunnel through the Gotthard, which is much faster and a better way. When we now see on the table the spectrum of drives, we can see the tape will probably remain because there is a lot of data you just need for documentation reasons to have a proof that this test has once been done, and probably you will never need it again, but then it's important to store it. And here is the ideal platform is LTO with LTFS, linear tape file system, which is transparent, so you can take the cartridge, put it on any LTO drive and use it like a memory stick. So when it comes to disk, we see, okay, the nearline SAS and SATA, they will stay for capacity things with cold data or data between cold and hot, while we see the SAS 15K, they are gone because you have same or better performance with SSD. 10K is more or less a little bit a question of time until they will disappear, 2.5 inch. And the SSD SAS, we see also the SSD SAS are more or less same price as NVMe. And so why should I have stones in my backpack maintaining the SAS layer instead of having so many possibilities to take a shot away? So we see a movement to U2. M2 is a very good thing to have it directly on the motherboard as maybe a boot device, or since they are more reliable than other boot devices we had here, they may all be also taken into account for metadata because they're now going up to 1 terabyte already, the M2. So the main movement will be to the NVMe 2.5 inch, and as soon as ruler and NGSFF are broadly available, we think there is a migration of the U2, because U2 has more components, is not as efficient with thermal things. So there will be a migration to the upper technologies, or the upper interfaces, hardware interfaces. So we see the hierarchy of the technology, and I think it's easy to compare NVMe's like having flat screens compared to displays. It's just a question of time until the lower technology will disappear. Here's the problem that the manufacturers underestimated by their own the demand of the technology. So last year we had tremendous problems to provide those drives, but they have built up the capacity, and as soon as there are a little bit more players and competition, then we see more and more attractive prices again. And in the long run, I think we see on the top the NVMe. I think the SAS fiber channel drives, they are gone, because we have the SATA SSD, because they are much cheaper than the SSD. And if you don't need the high performance, then you can take SATA. It's more capacity questions. And maybe for a certain time we will also have the nearline SAS and SATA. But we should not forget what's the decisive criteria. The PCI bus is in the server. And only over the PCI bus we can really take full advantage of flash technology. Really server-centric more and more. Then on the development are 5 to 100 terabyte NVMe, probably more for cold data with lower disk write per day, things like this. Then we see PCI 4, but the example of those 50 to 100 terabyte is important to evaluate. Why do we need more bandwidth, or why do we need more lanes? Because if you have 100 terabyte on one drive, you need also some throughput to access a drive and to copy the drive. So then it may be helpful to have these at least 4 lanes of PCI 3, or then afterwards with PCI 4. Then overall, we should not forget that we become server-centric. And we may replicate, we have a cluster. And for this, we say we should create a low latency data drum in order to make replications between the storage of the servers, also having the server-server communication with low latency available. So instead of talking about north-south, east-west traffic, we created the expression data drum in order just to give the picture. It really has to be fast. So it's really an accelerator, and we should take into account and not forget about this factor, meaning when we design our server, also reserve some PCI slots for communication, and not book completely out with NVMe. This is a challenge. So then, I thank you for your attention. And here you see what are our main partners. With Lenovo, we do mainly the DSS spectrum scale machine with the software RAID. And Spectrum Scale and Spectrum Protect, we have a long tradition. It's now almost between 15 and 20 years. We use it in all kinds of environments. And so these are the main players in this domain. So if you have questions, please ask, or I'll be around also the rest of the day.